Production of phenylamine. Phenylamine can be produced by reducing nitrobenzene. The reactions will involve the use of tin, because tin will be the reducing agent, and tin typically is used because it can, for every 1 mole of tin, it can give up to 4 moles of electrons, because 2 moles when converted to Sn2 plus, another 2 more moles when 2 plus is converted to Sn4 plus. This is relative to iron or zinc, because in the case of zinc, at most every 1 mole of zinc can only release 2 moles of electrons, while 1 mole of iron can at best only release 3 moles of electron. So the half equations for nitrobenzene being reduced to form phenylamine is indicated here. So by actually adding up these half equations, you are able to derive the full equations when tin reduces nitrobenzene to form phenylamine, and the byproduct being Sn4 plus. And the conditions for reduction of nitrobenzene to phenylamine is to reflux with tin, in the presence of con HCl, and thereafter excess NaOH to be added, because with the presence of con HCl, the amine produced will be neutralized to form NH3 plus, and therefore by having excess OH minus, you will help to neutralize the NH3 plus to form NH2, phenylamine. Let's take a look at some of the separation technique that involve phenylamine. It's important to note that phenylamine is a liquid at room temperature, slight orange in color. Phenol is a solid, while benzene is a liquid as well. So the way to actually separate this is first to add NaOH, because by doing so, your phenol is converted to sodium phenoxide, which is ionic, and therefore it will go into the aqueous layer, while benzene and phenylamine are in the organic layer. And using a separating funnel, you can separate the aqueous from the organic layer, and from the aqueous layer, we could acidify the aqueous solution with acid, followed by actually evaporation and filtration. You'll be able to extract your phenol. In the case of phenylamine and benzene, we can further separate them by adding dilute HCl. And since HCl is an acid, you will be able to neutralize with your phenylamine to form the phenyl ammonium chloride, which is ionic, and therefore highly soluble in the aqueous layer, while your benzene stays as an organic layer, and you can split them using a separating funnel. To neutralize, you can then add excess dilute NaOH and neutralize phenyl ammonium chloride to form back phenylamine. Let's take a look at the chemical properties of phenylamine and vis-a-vis that of phenol. So in terms of their state, phenol is solid, phenylamine is liquid. In the presence of sodium hydroxide, phenol dissolves as phenol is acid, but phenylamine is a base, so no reaction. In the presence of aqueous hydrochloric acid, phenol is an acid, so no reaction. Phenylamine dissolves. In the presence of aqueous bromine, phenylamine and phenol both have OH and NH2 groups, which are strong ring activator. So they will be able to activate the benzene ring, which means you can see that both of them are able to undertake full substitution. In the case of bromine in CCl4, there will only be monobromination. In the presence of corn nitric acid, you will get full nitration in the case of phenol. However, phenylamine would neutralize with the corn nitric acid to form your phenyl ammonium ion. And phenyl ammonium ion's lone pair is no longer available to act as a nucleophile, since it already accepted a proton. Therefore, we expect the yield of this product to be poor. Do take note that to produce 2,4-dinitrophenyl ammonium nitrate, you still need concentrated sulfuric acid as catalyst. In the presence of dilute nitric acid, you'll get mononitration with phenol, but in the case of your phenylamine, it will just be a neutralization reaction, and the salt that you get will be phenyl ammonium nitrate. Finally, for QA tests, you remember that for phenol, we add aqueous neutral iron 3 chloride solution and get a violet complex. But in the case of phenylamine, you add sodium nitrite in the presence of dilute hydrochloric acid, less than 5 degrees, followed by phenol to get a bright orange precipitate. This is another reactions that involve starting with phenylamine, reacting with acid chloride to produce your N-phenyl ethaneamide. So this is ethaneamide, and phenol is because the phenol group is bonded to the N. So therefore, it is N-phenyl ethaneamide. Thereafter, with actually the amide group, and amide group is a 2,4 director, you'll find that you can then add your aqueous bromine, where you will get bromination, and thereafter you can do alkaline hydrolysis to then produce this compound. This is the step that you will follow to get only a mono bromination. If, for example, you decided to put corn nitric acid together with phenylamine, you will get full nitration. Let's take a look at another example. In the other example that we have, we also start with phenylamine, and then we want to also similarly produce your N-phenyl ethane amide. In this case, we will also add acid chloride, and thereafter we can add corn nitric acid, corn sulfuric acid at RTP, where in this case, like we mentioned, the NH group here, the amide group here is a 2,4 director. So therefore now your nitro group can be at position number 4, and thereafter we can do the hydrolysis where you end up with your 4-nitrophenylamine. Finally, let's take a look at these two examples. In these two examples, the key thing to note is that this is a strong ring activator, and it is actually a 2,4 director from the data booklet, while this is a very strong ring deactivator, and from the data booklet you'll notice it is a 3 director. So with that, let's take a look at the Cl as the electrophile. So with respect to your amine, is position 2, which is here, and position 4. So the Cl will be directed there. If we were to now examine from the perspective of your nitro group, which is a 3 director, it will also direct the chlorine to this position and this position. Hence, because of that, in the exam, this will be the final product that you get. Finally, in this table, what we have here is all the reactions that you've learned for electrophilic substitution of aromatic compound. We start off by looking first at benzene. So benzene, you'll learn about these two conditions. And thereafter, if you take a look at your methyl benzene, and knowing that methyl activates the ring, you'll find that the temperature for nitration could actually be lower. And finally, when you actually nitrate and halogenate your phenylamine and your phenol, knowing that they are strong ring activator, that means that you just need to use dilute nitric acid for mononitration and concentrated nitric acid for full nitration. Similarly, you just have bromine in CCl4 for mono and aqueous bromine for full halogenation. There's no need for any catalyst at all. On the other hand, when you look at actually your halogenorine, it's actually a weak deactivator, or it deactivates the benzene ring. It's a 2,4 director. So you can see that these are actually specifically its condition. And last but not least, for nitrobenzene, bear in mind, it is a strong ring deactivator. And therefore, in the reactions itself, you need to have reflux or heat at high temperature. Finally, we have a ring of compounds that's here. These are the moderate deactivator, whereby the C double bond O group or the CN group are all electron withdrawing. So they would also need reflux at high temperature. So in the conditions required for halogenation or bromination, they will still need reflux or heat at high temperature. Conversely, if you look at N-phenyl amide, which is the example that we have earlier, your NH group, which bonds to benzene, is a ring activator. So therefore, because of that, it is actually a 2,4 director, and it activates the benzene ring. Do note that this is therefore a ring activator, while if you have your CO bond that bonds to the benzene, that is a ring deactivator.